Good evening, everyone. First of all, thank you everyone for joining the
So
session.
today's session basically will discuss about Spin Qubit Semiconductor by one of our engineer, that Ujjwal Pratap Singh. So he will deliver a small presentation and some tutorials also on nanoscale, that spin nanowire application, qubit simulation by using QTCAD software. So Ujjwal, you can start your presentation session, please, and try to provide some knowledge about the different product that we have, please.
Thank you, sir. Good evening, everyone. First of all, thank you for joining the session. I'm Ujjwal Pratap Singh from Impulse Technology. I welcome you to the
Good evening, sir.
third day of FDP program. In today's session, we will learn about the quantum computer-aided design tool. Before moving further, let me brief about our company. Impulse Technology is a distributor of next-generation technology simulation software, like in nanotechnology, nanomaterial, solar cell, organic LED, and lot more. And we are partner with multiple companies. Like first one is Nano Academic. Nano Academic is a Canadian-based company which will offer some software. Like first one is Nanodcal. In Nanodcal, you can perform the modeling and simulation of nanoelectronics, nanowire, and nanomaterial like carbon nanotube, spintronics device, solar cell, and lot more. Second one is Rescu. In Rescu, you can perform modeling and simulation of large-scale DFT, nanomaterial, nanoelectronics, and you can study on electronic structure, crystal structure, device structure builder, lattice parameter. And the third one is QTCAD. You will know more about in upcoming slide. And the second company is Fluxim. Fluxim is a Switzerland-based company which provide world-class software and hardware for photovoltaic device like perovskite, tandem, thin film, and organic and light-emitting diode, quantum dot LED, OLED, and perovskite. And third one is Metra. It is a cloud-based material simulation software. And talking about services, we are a software distributor of next generation technology simulation software, training program with our experts. We also provide technical support and we offer some equipments such as probe station, testers, and regular setups. And our valuable customers are top finance institute of India, such as IIT Madras, SRM Institute, IIT Guwahati, and lot more important institutes. Moving to our tools, it a QTCAD, a quantum technology computer-aided design tool. Quantum technology computer-aided design tool is a finite element matter simulator used to predict the performance of a spin qubit device before their production. Our advanced spin qubit modeling tool, it comes with features like an electrostatic tool that solves the confining potential of quantum dot in semiconductor nanostructure and find corresponding envelope function for electron or holes, where find the probability of where electron or holes in quantum dots. And second one is value splitting calculation tool. Its purpose to compute the energy difference between different quantum states in silicon-based device. In some material like silicon, the electron exists in multiple value. These tools help calculate the splitting difference between these values. Critical for silicon qubit stability, help optimize quantum dot behavior. And the third is the exact tabulation tool for the treatment of Coulomb interaction in few electron system.
So is clear not visible.
What? Is my screen visible?
Yes, it is visible. You can carry on.
Yes, sir. Now it's visible, sir.
Is an exact tabulation tool for the treatment of Coulomb interaction in few electron system. Its purpose to simulate how electron in with each other through Coulomb force, analyze few electron system by solving equation to predict how electron behave when they are close and affect each other. Focus on electron interaction. And the fourth one is a master equation solver for quantum transport calculation in the sequential tunneling regime, and find the treatment of Coulomb blockade and the calculation of charge stability diagram. Its purpose to model how electron move when tunneling occurs. And the fifth one is an electron dipole spin resonance module that interfaces with theory for the time-dependent simulation of quantum controls. And the sixth one is a painless treatment at cryogenic temperature of a several design of solid-state spin qubit. It is used to model quantum device at cryogenic temperature, which is necessary for quantum computing. It's handled the design of a solid-state spin qubit, which works best in ultra-cold environment, and the user-friendly Python application programming interface to launch the simulation. And it's also compatible with device in an open source Python API that defines gated quantum dot geometry from gate layout. If we're talking about technology background, how spin qubits in semiconductor, it basically confines single electron or holes in a quantum dot in semiconductor heterostructure. Use a spin degree of freedom to implement qubit. Inside this symmetry diagram, we see silicon germanium heterostructure, which confine electrons, which create a quantum well, and manipulate single spin qubits with microwave and perform two qubit gates and by exchange interaction. About the technical advantage, is a small nanometer size circuit able to fit millions of qubits on a single chip. It also can operate at 1 Kelvin. This is a natural continuation of today's semiconductor technology. It also leverages manufacturing capability of the semiconductor industry. And we talk about companies like Intel, Global Foundries also work in the field of quantum chips. If I talk about what are the technical challenges to the design for the quantum chips, it is difficult to engineer a chip that confines single electron. It is difficult to make qubit for a confined electrons. Study a large set of devices until finding the desired property in costly in resources in money and time. It's also difficult to understand the physics behind the experiment data from measurement performed on devices. Designing a model specific to particular device is costly in time. Lack of general simulation for semiconductor qubits is solved by our tools like QTCAD. Streamline the design process with reliable all-in-one tool for simulating spin qubit quantum components in laboratory conditions. It's applicate the real-world scenario for advanced communication solutions, security, and quantum computing devices. If we talk about TCAD and QTCAD, in TCAD we use classical physics, and in quantum technology computer-aided design we use quantum physics, and the performance matrices are also different. We use Rabi oscillations and probability of states. The main challenges of a spin qubit simulation, if we talk about transistor device, it works room temperature operation 300 Kelvin. It's work cryogenic temperature operation, significant challenges to solve a convergence. In a transistor device, it's many electron regime, but in spin qubits, few electron regime, ideally one or few per qubit. Either quantum confinement is correction. In the transistor device, no quantum superposition or entanglement. In the spin qubits, quantum confinement, superposition, or entanglement operation principles. Conventional TCAD software is not suitable to design the quantum hardware. If you talk about benefit of QTCAD, it's from device layout to qubit performance matrix, how we import the files and other. Use Python-based device generator to import geometry from the gate layout, like GDS files, and export arbitrary device geometry. Use QTCAD to better understand experimental results with real devices and calculate key spin qubit performance matrices before manufacturing your devices. Our competitive advantage is adaptive matching, which helps for better results. Its robust convergence of a cryogenic temperature at electrostatic below 10 millikelvin. Quantum mechanical models are also essential to predict spin qubit behaviors. If we talk about unique feature of QTCAD, its work at cryogenic temperature and Schrödinger solver also present based on effective mass KP theory. Many body and master equation solver for charge stability diagrams. It's also present value coupling, quantum wave physics, and Rabi oscillations, micromagnet ESDR. Also predict Rabi frequency and leakage from the device geometry and input magnetic field gradient. And tunneling coupling exchange, non-equilibrium function is also present. And additional features are point charge effect, lever arm matrix, strain solver, and it also supports Jupyter Notebook. If you talk about QTCAD workflow, the first step is a device specification. In device specification, we define the geometry, dimension, and shapes of the geometry. Like in this example, we take gate all around field effect transistor. Second step is mesh. In mesh, we define convert the mesh into GMesh, is a third party open source. After that, we use QTCAD to define the materials, doping, gate, boundaries, and after that, we visualize and analysis using PyPlot, PyVista, or ParaView tools. If you talk about QTCAD models, first we create device geometry from gate geometry from layout file, heterojunction, and design rule from the Python API. More complex 3D geometry from the GMesh. And then after that, we give electrostatics, define boundary condition, ohmic sort key, and applying potentials, and define doping densities, and also solve nonlinear Poisson equation and get Fourier confinement potential in quantum dot. And after that, we solve Schrödinger solver to find effective mass and get envelope function and eigenbasis, and also find the probability of electron or holes in quantum dot and get levers arms. After that, we solve many body solvers to assemble many body Hamiltonian operator to find total energy of the systems and exact diagonalizing in truncated basic sets and get many body eigen energy and eigenfunctions. After that, we quantum dynamic features get a Hamiltonian corresponding to the realistic device geometry and interface with QTIP to calculate quantum dynamics and calculate Rabi oscillations, micromagnet or spin orbit, and get fidelity. After that, we transport features master equation solver in sequential tunnelism to get transport peaks and how charges move, including Coulomb blockade. If we talk about use cases of QTCAD, there are many publications and scientific papers that have been published through QTCAD tools. Like first one is robust technology computer-aided design using QTCAD tools. And if you search in Google Scholar, there are many these publications have been published through QTCAD tools. Like the understanding condition for a single electron regime, 28 nanometer FDSOI, quantum dots, and experimental data with 3D quantum ticket simulations. If you go through papers, they use QTCAD tools to find Coulomb blockade, numerical and experimental observation of side gate state. Our first example for the simulation is nanowire quantum dot simulation. The primary objective of this simulation is to analyze the electrostatic property and confinement effect in nanowire quantum dot using Poisson and Schrodinger solver. In this, we use nanowire and quantum dot. A nanowire basically is a one-dimensional structure with a diameter in nanometer range, and length is significantly larger than its width. And material, nanowire can be made from semiconductor, silicon, gallium arsenide, metal, or insulating materials. And talk about properties, this makes them ideal for miniaturized device, quantum confinement, where electrons are confined in two dimensions, leaving one dimension along the wire for a conduction. In the same way, a quantum dot is a zero-dimensional nanostructure confined by electron in all three spatial dimensions, typically 2 to 10 nanometer in diameter, is smaller than the electron de Broglie wavelength. Its property discrete energy level like those of atom earning the name artificial atoms. And talk about the structure, it's a cross-section area where it's two concentric cylinder. The inner cylinder is filled with silicon and then silicon dioxide and then gate, which is a metal. And here we cut plane along the channel, which is source and which is p-doped, and drain which is also p-doped, and channel is undoped. And we have talked about using two solver, Poisson and Schrodinger. In this Poisson solver, calculate the electric potential in a semiconductor device. It's also take account into doping concentration, how the number of added impurities in the semiconductor, and applied voltage, like gate voltage in a transistor. And it also uses Schrodinger solver to deal with the quantum mechanical behavior of electron in a transistor. In like nanowire, quantum mechanics has started to play a huge role because electrons behave like a wave, not just particles. The Schrodinger solve help calculate these electron wave move and interact inside the transistor, where the electron is most likely to be and its energy level. This is essential for understanding the device performance at nanoscale. To unlock the full potential of nanowire technology, both classical and quantum behavior must be understood, and that's where QTCAD powerful simulation toolkit for the next generation transistor design. The process should be like first we create mesh which using geometry file with and nanowire. Then after that we set command create which create GMS file. And after that we device setup. In device setup we create Python script where we define some modules, some parameters, materials, and region like silicon for the channel, silicon dioxide for oxides, and boundary where ohmic at source, drain gate at the channel surface. And we use two solver, Poisson solver and Schrodinger solver. In Poisson solver, we compute electrostatic potential for by self-consistently solving Poisson equation. And in the Schrodinger solver, we calculate quantum confinement effect in the conduction band. And we execute after that mesh loaded device created and some band structures and solver executed to achieve convergence. Let's jump to the simulation part. First, we create, if we go through the workflow, then first we create geometry of the file. It's in the QTCAD where I created earlier. nanoy.go. By running this command in terminal window, It creates the geometry of nanowire. It contains two concentric cylinders. In a cylinder is filled with silicon, then silicon dioxide, then metal, and the one end is source and the other end is drain. If we go to geometry mesh file, it's a 1D using points and define the surfaces. We create a geometry. It's 2D structure. And its 3D structure. After calling that, it created mesh file. We go to the same folder. It created the mesh file of the nanowire.msh extensions. After that, we go to the Python script where you import some modules like constant for universal physical constant like Planck constant, elementary charge. And we also import from QTCAD device mesh where we're defining the mesh points. And we import in IO file where you import input and output from other files. And we also import analysis for plotting the graphs and analyze the. And you also import material from QTCAD device. And we import device always. And we import two solver, Poisson solver and Schrodinger solvers and their parameter as well. After that, we define some parameters like gate source bias where 0.5, and then we metal work functions, and we define the device height and device radius. And we also define part to mesh file and output files where we did store in the folders. And we also load the mesh. And it plot the mesh using this command mesh.show. After that, we create device from mesh and set statistics where use Fermi direct and Fermi direct Boltzmann approximation. They determine the boundary values. Failing to do so will produce inconsistent result. And we also use Fermi direct approximation. And then it creates region first. Here we define regions like silicon dioxide for channel, source, and drain. And here we define the doping concentration. After that, we create boundaries like source, band, drain, then after gate. And after that, we create and configure solvers like Poisson solver parameters and tolerance, define the tolerance. After that, we use self-consistent solution, which iterate up to the tolerance level. And after that, we define some electron hole and hole densities and conduction band and valence band. And after that, we load some variable into IO files. After that, we line cuts along with Z with X, Y, 0 for the same quantities. In the same way, we import some line cuts and plot the line cuts. And we plot band diagram also. And we also calculate Poisson solvers. And after that, we use Schrodinger solver with their tolerance and use some parameters. And we also print energy of the levels. After that, you use plot hole and hole densities. Let's simulate the needed. Take times. Here is mesh created. It's cut into manageable sections where all solver will be performed. Is solving Poisson equation with boundary condition. After that is Poisson iterations. After that, it create file sum. like create electric potential, then create band diagram where it's conduction band, Fermi level, and valence band. Then it's create whole densities, creates potential after the ground states, then it creates first excited state, then second excited state, and simulation will be done. If you look above, it create Poisson iterations as well, solving Poisson equation with the boundary condition. And here 3D mass statistics. So the total number of elements, tetrahedral elements, and region physical name. And all the file will be stored in the same folder, QTCAD. Then go to the example and output folder where it create nanowire line cuts, nanowire.vt file, nanowire.hdf file. Let visualize into ParaView. Go to the file, then open nanowire.video. It create nanowire, and if you analyze through, like conductions, valence, electrons, so ParaView you can analyze and whole densities. Let's move to the presentation for second simulation. In this simulation, we quantum transport phenomena is silicon on insulator, basically fully deflated silicon insulator containing a quantum dot using the non-equilibrium gain function to formalize combined with Poisson equations. Basically, we use non-equilibrium gain functions where is a quantum mechanical method to describe the behavior of electron in a system that is not in equilibrium. In this simulation, NGF is used to compute the charge density, how the electrons are distributed across the device under non-equilibrium condition when the device is operating with voltage bias applied, and also a quantum effect like tunneling, interfaces, and the discrete nature of energy level, which are important in nanoscale device like this FET. And we use a fully depleted silicon insulator geometry. Here you use FDSOI refer to the type of semiconductor structure where a thin layer of silicon is placed on top of a insulating material, typically silicon dioxide. In this case, the silicon layer is fully depleted of a charge carrier when the device is in off state. This helps reduce leakage current and improve performance in smaller devices. Step in this simulation will be like first we define device geometry, like create geometry of the file. Like you use silicon nanosheet, which is active channel, then source drain heavily doped for electron, channel undoped, then oxide layer, and metallic gate, like barrier gate which control the electron tunneling, plunger gate alter quantum dot energy levels, and backgate with module potential by fluoride oxide layer. After that, we create mesh construction, which divide the device into smaller element for numerical computation. After that, we define the simulation using device setups, device object, which represent a transistor in Python scripts. Temperature set to 0.1 Kelvin for the quantum effects. Charge type focus on dopant and quantum electrons, and also define material properties like source, drain, ability of silicon, channel, pure silicon for quantum effects, and oxide, perfect insulator. And we also define boundary condition. The same way backgate, Fermi's level set for the real world biasing, and the top gate set voltage to define quantum dot potentials. After that, we define some NGF parameter. We use NGF solver and mixing parameter for balance, stability, and convergence speed. And we solve the devices using iteration method and compute electric potential, compute charge density, and repeat until convergence. And after that, we using post processing. Let's jump to the simulation part. I created earlier this file. In this Python script, we import some libraries, we import some modules like constant for universal physical constant, elementary charge, and we import some mesh, sub-mesh, and import material, device, sub-device, and sub-solver like NGF solver. And after that, we set the path for the files like message and outputs. And after that, we load the mesh. And after that, we define the device objects when set the temperature 0.1 Kelvin. And after that, we create the regions like hand doping. And after that, we define some new regions like top silicon dioxide with channel, source, and drain. After that, we set boundary condition for the backgate, where we set backgate bias, doping backgate, and binding energies. After that, we set boundary condition for source and drain of FET and NGF simulations. After that, we calculate the charge density on a device. Here you use NGF Poisson solver parameters. And after that, define parameter to line curves over which various quantity will be plotted. After that, we define the voltage corresponding to off state, sequential tunneling regime, and on state also. After that, we set the boundary condition for the top gate. After that, you use NGF Poisson solver and solve and plot, say, various quantities. And you use conduction band age and its local density of state also. It's all print value in the investigate. Let's run. First, we load the geometry of the FDSOI. Create the geometry that I created earlier. There are 3-gate, plunger gate, pack gate, and if you define one dish, it look like that in 2D. Three D. This simulation take too much time. That's why I did earlier, and I saw the result. It's create output, it stresses and also show computation time. After that, it's plot some band states like off states, sequential tunneling, and on states. After that, it took some graphs of states with energy electron volts with distance in nanometers. It showed band age, source Fermi level, drain Fermi levels, and sequential tunneling, and also on state. After that, it's some electrical current with energy graph in off states, in sequential tunneling, and in on states. Let's some simulate other example as well. In this, we use import some modules. After that, we define some parameters, and in the same way, we load the mesh and set the temperatures and create device regions, create device boundaries, and configure the non-linear Poisson solvers. Just load the mesh file. It's adaptive meshing. Basically, it's create a smaller section where convergence is mostly needed. And after that, it create 3D mesh statics like total number of elements, triangular elements, and total number of nodes, and solve Poisson equation with boundary conditions. And it's also solve Poisson iterations. And create an load band diagram with conduction band, valence band, and Fermi level. If you go to the nano-academic side, we go below, we go documentation tutorial, where you get QTCAD documentation and tutorials. Like in introduction, we find features of QTCAD. After that, installation process, license activations, and how to start, and theory parts, like which solvers are there, like Poisson solvers, coordinate solver, band alignments, which band alignment adapter loans, lever calculators. And here are some tutorials also, like in device package, Poisson and its coordinate simulation of nanowire quantum dots. You can take reference from there. And also transport packages and qubit packages. If we go to the practical application, here are some example are present. Like first it create a device, then Python scripts. From that, it create top view and side views. Like Poisson solver with background charges. Firstly, it creates a geometry file. Then after that, we load the mesh using Gmesh. Then after that, we script. By running this script, there are solvers like Poisson solver and Poisson and Sconinger simulations. Let's back to the presentation. If you talk about the difference between quantum technology tool and Silvaco, the traditional TCAD software, in QTCAD we use qubit simulation basically, but in Silvaco it's not available. In the same way, quantum dot simulation is present in QTCAD, but in Silvaco it's not available. In the same way, value splitting calculation tool is also available for the silicon-based qubits, but in Silvaco is not available. In the same way, quantum transport calculations like quantum transport, Coulomb blockade is present in QTCAD, but in Silvaco or Centaurus is not present. You can do cryogenic temperature simulation in QTCAD up to 10 millikelvin, but in Silvaco it's not possible. In the same way, electric dipole spin resonance is also available in QTCAD, but in Silvaco it's not available. It's also available quantum control in QTCAD, qubit control via external feeds, but in Silvaco it's not available. In the same way, it's Coulomb electric interaction modeling. It's in Silvaco not available. It's come with multiple features. If you talk about the future directions, basically defects and roughness is of impact charge stability diagram and single qubit gate. We also upcoming in features 2 qubit gates and scaling to the large quantum dot array and multi-scale simulation. And we also integrate with TFT. Let's run some more example. Um, let's run the background charges where we define some parameters and modules. And firstly, we load the GMS files. Some errors. Try it again. Nano web background. Create a symmetry of nanowire background charges. After that, he loaded the mesh file into folder. It created two files, a nanowire background charges unrolled file and nano background charges .mesh files. If we run the program, then explode 3D mesh statistics, loading mesh files. All calculation happen in the mesh file. It's all non-Poisson solver with background charges. Some relate to error and error thresholds. Some Poisson iteration happen. So 12 Poisson iterations and computation times. It's load with background charges and without background charges. And it's create and simulation done. And you can also see the playlist of our channel where we taught about QTCAD tools. You go to the playlist section, then there's QTCAD playlist where you demonstrate multiple like QTCAD installation process, quantum technology, spin qubit semiconductor devices, and Poisson correlational simulation of graphite, and some demo. And if you have any query, you can unmute and ask some query.
So, dear participant, today's session basically was on spin qubit semiconductor devices based on QTCAD software. Now we have given, our speaker have given some information, right, about different type of examples. Ujjwal, can you hear me?
Yes, sir.
Okay, perfect. So basically, Ujjwal have delivered the talk on different examples he tried to run and show you some presentation on spin qubit semiconductor devices and some basic things he have tried to deliver. Now I would like to share my screen and I would like to show you something. So just a minute. So if you want to also explore this QTCAD tool, specifically for quantum domains applications, so you can also scroll many tutorials. Okay, theoretical background is also there, that on what basis the software will perform various equations. So the theoretical information is also given, that various solvers are already implemented, like Poisson, Schrodinger's, Copley-Belling effect, many-body solver, and charge transport in Coulomb blockade regimes, and NEGF formulae, including quantum controls. So these are the multiple tutorials which you will open it. Then you can get to know many things about the software in details, because 1 hour session cannot give you everything in the deeper insights. So we will suggest you to go into the details by referring this documentation page. In the documentation page, you can get to know many things about the background equations, whatever the tools, the component required, the simulator required, the visualizers, the mesh creators, or whatever the packages required to solve different devices. So this is like one of the Coulomb blockage tutorial. So the physics, whatever the company have developed, that information, fundamental information, are given in our tutorial page. Okay, so we can already given the link in past. So even still we can give you on the chat box, so people can scroll there more information. And even we will also have more webinars in coming time on the QTCAD on different applications. But before that, if you want to know about this quantum control application in QTCAD, or electrostatic dipole spin resonance analysis, so you can open that particular link and you can find how this QTCAD can perform different kind of applications. Either you want to perform the charge analysis, charge noise in quantum dot. So this is one of the tutorial where QTCAD is a basic software component requirement. Mesh file is already generated from the GMesh. Python script is written in the VS Code. So it is a Python scripted software. Okay. User interface is under development. So company are developing various theoretical codes as well as some background user interface, so that you can also create it quickly, because it is a emerging sector. So company are developing a lot of new features parallelly. So in the meantime, you can scroll these all information from there. So whatever the related to noise related application, quasi control, noise analysis, electric dipole spin resonance analysis. So if you want to work on that, you can scroll this. So proper information where gated type of device you want to model. So it will start from K layout to model your layout of your structure. Then GMesh will create the meshing structure, and then it can run your mesh, and then you can run your script. You can modify or you can manipulate the script, whatever given in the example. You can create your own scripting in our VS Code, and then you can also perform different icing apply or different gate thickness, different material, custom defined material you want to use. We have our own material library. You can define that material parameter, and we have a visualizer, P by Vista and ParaView, for visualization of the different devices. So that's why this documentation page, I believe it will be very helpful to give all the insight, all the information, whatever the output are generated, that information related to ground state, single excited state, single qubit device, multi-qubit device, and other applications. So all the information you can, details are given there. Okay. So you can also see the noise related parameter and electric dipole spin resonance and Rabi oscillation analysis. Okay. So these are multiple documentation page and tutorial page. Okay, so you can look into that. It will be definitely give you some insight, and still you will have some query. Then we can have a more one-to-one discussion on particular your problems that you are working on it. Okay, and apart from that, as you know, the couple of tutorial is also there apart from the theoretical backgrounds. So if somebody want to work on device related application, we have a QTCAD device package. Those who works on quantum transport, we have a QTCAD quantum transport. Those who works on qubit application, we have a QTCAD qubit package. So these three packages are there. These are all device specific examples, device specific tutorials. So either you are working on GAFET, so this first tutorial, nanowire quantum dot GAFET, adaptive meshing are there to solve your meshing accurately on the particular interface of your materials. Poisson solvers are there, adaptive meshing with different solvers, Schrodinger band alignment in different heterostructures, visualization of your output, MOS capacitor is there, Schrodinger simulation of quantum bell. If you want to work on quantum bell, that is also possible. Multiple quantum bells, spin orbit coupling with magnetic effect, strain in the simulation, Bailey coupling, many body analysis of nanowire quantum dot, FDSOI transistor simulations, and multiple plumber gate, tuning the barrier gate, perturbation theory, exact diagonalizations, and point charge defect in double quantum dot in FDSOI. So these are multiple device package in QTCAD. And next package is called transport package, where you can work on quantum transport master equations, WKB approximations, charge stability diagram of double quantum dot, NEGF simulation, FDSOI and transistor, and electric dipole spin resonance dynamics and electric dipole spin resonance for noise analysis. And there are so many paper is also published on that. So if you see the website of this Nanotechnology technology, there are a couple of publication. So just a minute on different quantum related analysis. So you can see this is nanoacademic.com. Click on technical insights. In the technical insights, you can go there, bibliography section, and select the QTCAD, and it will show the papers published by using QTCADs. So this is one of the paper where from first principle modeling of single lunar spin qubit devices, where based on Rescu software, the material property are calculated and then the qubits were simulated by using QTCADs. So Rescu as well as QTCAD single paper in this particular papers, they have used the QTCAD as well as Rescu software. You can find some other quantum sensing related papers, nanoscale single electron box with protein lead for quantum sensing. So this is one of the paper. These are all latest paper. As you know, there are very few qubit softwares are available in the market. And this is one of the very first commercial tool which working on qubit simulations. So either you are working on 3D TCAD application for industrial compatibility of FDSOI and many other single PBS colloidal quantum dot transistors, modeling of noisy quantum computers, spin qubit in semiconductor. So this kind of papers is also published last years. So it is very rapidly developing the tools. Okay, so many papers are there. I believe this kind of tool will be very helpful for the emerging sector, those who would like to start their career beyond the nanotechnologies, because it will come to the next level of qubit simulations beyond the traditional TCAD or nano applications. And you can also scroll it, and some video is also available. If you look into our playlist library, where you can click on this qubit playlist, this is our some of the video are available. Okay, so you can scroll it and you can watch it. I believe some will be helpful. Now today's session for this QTCAD is enough. Tomorrow's session we will discuss about. I would like to tell you this Fluxim company. We will discuss about this Fluxim, that is a Switzerland-based company, which developed the software as well as equipment for simulation of solar cells, perovskite solar cells, tandem solar cells, thin film solar cells, and LEDs application, perovskite LED application, charge transport, ion transports, and many more applications related to solar and optoelectronics LEDs applications. So this will be delivered by one of our engineer, Mr. Sahil Barma, who will deliver the talk on this SATFOS for optoelectronics semiconductor devices, where LED and solar cells will be the cover up. Other product is also there. You can look into their information on this page, and we can also give you some more information in coming days how this kind of other equipment can also be benefited for your research. We want to see the tomorrow session. So I want to show you this this one of the user interface of SATFOS. So I want to open and want to show you one of the visualizer, graphical user interface, so that one of our speaker will deliver the talk on this thin film, solar cells, LEDs, multiple semiconductor layers based device simulations. So you can see this is multiple emitting layer, emission layer, multiple emitter layer, and one of the layer tandem perovskites, where number of layers will be like more than 10 layers, more than 20 layers when you want to simulate the perovskite based devices. So tomorrow session will be discussed on this software, SATFOS, where this kind of structure can be created, or we will start from beginning and then more functionality will shown to all the participants, where more than 10 layer, 15 layer, 20 layers, or single layers, ETL, electron transport, hole transports, active perovskite layers, multiple interface, open interface. So many things will be explored tomorrow onwards, and even in day after tomorrow and on Friday also. We have very upcoming talk on that emerging experimental and beyond this nano related application, whatever the other other features are developing in the background, that information will be delivered in the coming talk. So today's session, I would like to thank you for all the participants who has given the time. I understand today we have given the less time because QTCAD is the new and emerging softwares, newly developed software, but you can explore it, and we will try to help you, those who are interested in either Nanodcal, Rescu, or QTCAD. If any participants have any questions, I request you can unmute your mic and you can ask your questions, please.
Excuse me, sir. Could you please tell me about the charges for Fluxim or any SATFOS software? License about.
Yeah, I understood you have applied for the license. So the charges, if I talk about it, dependent on the module. Like in the SATFOS, modules are there. So if you click on the SATFOS, there are 4 modules. This is called like absorption module for optical calculation, temperature diffusion module for electrical calculation, and advanced optics module for ray tracing, texturing, nanoparticle, that kind of analysis, and emission module. So dependent on how many modules you require. Basically for solar cell, this absorption and temperature diffusion, 2 module can also work for basic solar cells applications. So we have multiple options: 1 year, 3 year, 5 year, 10 years validity. So subscription validity and number of module you require. Based on that, price will differ. So if I talk the basic package for 2 module, let's suppose you want to go for this 2 module for 1 year package, that will cost around 3 lakh plus GST, near about 3 lakh plus GST for these 2 basic modules for 1 year validity. Whenever number of years will increase, then there will be some small discount will also be provided if you will go for 3-year license or 5-year licenses. This is the minimum cost for 1-year license that I told you.
Sir, actually, we all are participants, not the institutionals. So, if is any possibilities to purchase this software in collective
Individual
modes?
is not options available. Why you should discuss with your supervisor or other collaborators who can get the software in their organization. You can collaborate them, and then hopefully somebody will get purchase, but not individual purpose. They don't offer the softwares.
Okay.
So hello, sir. This is Harshvardhan. Okay. So my query is that in any laptop like Core i7, Core i5, like it will install right softwares
Which software, first of all?
like so QTCAD softwares. Okay. Fluxium.
So this
So
Yeah,
like we can install any kind of software, right? In any kind of laptop, like the core versions.
Yeah, basically for Fluxium set first, it can work on like i5 or that i7 or i9. It can work on it with a 8 GB RAM or 16 GB RAM. It can work. But whenever you want to work on Nanodcal or Rescu, that is DFT based softwares. And that DFT based software usually require high-end computational powers. So at least workstations are required for DFT based softwares. And this QTCAD can also run on like i7 with 16 GB or 32 GB RAM is required. So smallest configuration, system configuration by in this set for software, and then beyond more configuration in QTCAD and more configuration required for Nanodcal and Rescu softwares, because this is one-dimensional set force based on drifted diffusions, which will solve your equations fastly. QTCAD will require two-dimensional FEM-based simulator. So FEM-based takes little higher time as compared to set force.
Sir. Okay, sir. Thank you very much.
Yeah.
So, sir, actually, I am planning to do project in so gallium nitride using so HAMT electrified transportation. Okay. So I'm just planning to do that. So it is based on the fabrication of devices. Okay. So so these softwares like it is useful for my project. I mean,
Yeah.
any kind of software for the simulation purpose.
This QTCAD software will be useful for that particular application. High electron
Okay.
mobility transistor, and
Yes,
this
yes.
QTCAD will be helpful for gallium nitride or other compound semiconductor based device application.
Okay, so actually, I selected for PhD in SRM University. I think you are at the collaboration with SRM University, right?
Right,
Yes, sir.
right.
Actually, now the December onwards, like my PhD will start. Okay, so it is really like helpful for me also. Okay, so like I will ask to my college or guide. Okay, so
Yeah.
I'll let you know, sir.
Yeah, definitely. May I know who is your guide there in SRM?
Sir, Dr. Augustine Fletcher.
Okay, understood. Okay, fine.
Actually,
You can
sir,
let.
so we will discuss and we will let you know in email. Sir, personally will contact with you. Okay.
Yeah.
So I will discuss with Gaidley first, and after that, so we will discuss with you, sir.
Okay, fine. No issue, sir.
Yes, thank you very much, sir.
Okay, thank you. So, any other participants have any other query? So thank you to all the participants for joining and giving your time. So I request you tomorrow, please join the session, same timing.
Thank you, sir.
Yeah, thank you to all, and we'll meet you tomorrow at 5 p.m. Okay.
Yes, sure, sir.
Yeah, thank you. Thank you. Bye bye.
Thank you, sir.